Late August 1945. Sagami Bay Naval Arsenal, Kanagawa Prefecture, Japan. American occupation forces discovered something extraordinary hidden beneath camouflage netting in a forgotten corner of the testing facility. A single M4 Sherman tank sat abandoned, its hull covered in Japanese technical markings, measurement notations, and test numbers painted in white across every surface. Serial number USA 3089452, built by Fisher Body Division of General Motors in Grand Blanc, Michigan, belonging to the Second Marine Tank Battalion. This tank had been captured intact during the desperate fighting on Saipan in June 1944, transported across 1,500 kilometers of ocean to the Japanese mainland, and subjected to the most comprehensive technical examination Japanese engineers could devise. What they discovered during those tests had shaken the confidence of Japan's military-industrial establishment to its foundation. The tank bore evidence of extensive disassembly and reassembly. Bolt holes showed fresh tool marks where Japanese engineers had removed and reinstalled components dozens of times. The engine compartment contained handwritten notes in Japanese documenting compression tests, valve timing measurements, and cooling system efficiency calculations. The transmission housing had been split open so many times that gasket material had been replaced with improvised substitutes. Every system had been examined, measured, tested, and documented with the meticulous precision Japanese engineering was known for. The results of that examination had forced Japanese military planners to confront uncomfortable truths about American industrial capability they had refused to acknowledge since Pearl Harbor. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Sherman represented everything Japanese tank design was not. Built with mass production techniques Japan could not replicate, powered by automotive technology Japan had never mastered. Designed with reliability principles, Japanese engineers had considered unnecessary luxuries. American occupation personnel found shelves filled with technical reports documenting Japanese test findings, each report more alarming than the last about the industrial gap between American and Japanese manufacturing capability. These documents, written for senior Imperial Army officers and naval technical staff, painted a devastating picture of Japanese inadequacy in the most fundamental aspects of mechanized warfare. June 20, 1944, the island of Saipan in the Mariana Islands chain. Marine Corps tank crews from the 2nd Tank Battalion fought through dense jungle and fortified positions as Japanese defenders contested every meter of volcanic rock and tropical vegetation. The battle for Saipan represented one of the bloodiest campaigns in the Pacific War, with Japanese forces determined to hold territory they considered part of the homeland itself. In the chaos of close-quarters combat among sugarcane fields and civilian settlements, several American tanks were disabled by Japanese anti-tank guns, infantry attacks, and mechanical issues caused by the brutal terrain. One Sherman from Company C became separated from its unit during heavy fighting near the town of Garapan. The tank had taken a hit to its track from a Japanese 47mm anti-tank gun, immobilizing the vehicle in an exposed position. The crew, facing encirclement by Japanese infantry, made the difficult decision to abandon their disabled tank rather than be captured or killed defending an immobile vehicle. They destroyed the radio equipment and removed the breech block from the main gun before withdrawing on foot toward friendly lines. The Sherman sat abandoned for 3 days while the battle raged around it, neither side able to secure the position long enough to recover or destroy the vehicle. Japanese naval personnel from the Yokosuka Special Naval Landing Force reached the disabled Sherman on June 23 after American forces had pushed forward past the position. Engineers examined the track damage and determined it could be repaired with materials available locally. They fabricated replacement track links using machine shops on Saipan, installed the repaired track, and successfully started the Continental R975 radial engine, which had sustained no damage. The Sherman rolled under its own power to a temporary Japanese repair facility near the coast, becoming the first intact and operational American medium tank to fall into Japanese hands during the Pacific War. The capture represented an intelligence windfall Japanese military planners had sought since American tanks first appeared in combat at Guadalcanal nearly 2 years earlier. Japanese forces had examined destroyed Sherman hulks before, studying armor, thickness, and gun characteristics from burned-out wrecks. But those examinations provided limited insight into the mechanical systems that made American tanks function. This captured Sherman offered something far more valuable: a complete, functional vehicle that could be driven, tested, and thoroughly analyzed to understand American automotive engineering capability. Japanese Navy officials immediately recognized the strategic importance of this capture. Orders came directly from the Navy Technical Department in Tokyo. The tank must be transported to Japan for comprehensive examination at proper testing facilities with equipment and expertise unavailable on Saipan. Engineers fabricated a specialized cradle to secure the Sherman for transport, calculating weight distribution to ensure the tank could be safely loaded aboard a naval vessel. The operation required careful planning, as American submarines controlled the waters between Saipan and Japan, making any sea voyage extraordinarily dangerous. On July 2, 1944, under cover of darkness, the Sherman was loaded aboard the fast transport submarine I-36. The submarine had been modified to carry special cargo, with reinforced deck structures capable of supporting heavy loads. The Sherman was secured on the forward deck, covered with canvas and lashed down with steel cables to prevent shifting during the voyage. The submarine departed Saipan before dawn, beginning a perilous journey across submarine-infested waters to reach the Japanese mainland. The voyage took 11 days, with the submarine traveling submerged during daylight hours and surfacing at night to make progress while recharging batteries. American naval forces controlled the Central Pacific so thoroughly that even this specialized mission faced constant danger from patrol, aircraft, and submarine hunter-killer groups. The I-36 reached Yokosuka Naval Base on July 13, 1944, successfully completing one of the most unusual cargo missions of the Pacific War. The Sherman was offloaded and immediately transported to the Sagami Bay Naval Arsenal, a facility specializing in weapons testing and technical evaluation located 30 kilometers south of Tokyo. Japanese engineers had prepared testing protocols during the submarine's transit, designing comprehensive examination programs that would reveal everything possible about American tank design and manufacturing capability. The scope of the planned examination reflected Japanese desperation to understand why American armored vehicles consistently outperformed Japanese designs in every combat encounter. The technical team assembled at Sagami Bay represented the finest engineering talent available to Japanese military industry. Specialists from Mitsubishi Heavy Industries, which produced most Japanese tanks, joined engineers from the Navy Technical Department and academic experts from Tokyo Imperial University. These men possessed extensive theoretical knowledge of automotive engineering and metallurgy, having studied at prestigious institutions and worked on Japan's most advanced military projects. What they were about to discover would challenge their assumptions about Japanese industrial capability and force them to acknowledge that American manufacturing had achieved maturity. Japan could not match despite years of military expansion and industrial mobilization. Initial examination began on July 15, 1944, with photographic documentation of every external feature. Engineers measured armor thickness at dozens of points, recording variations in protection across different hull sections. They documented weld quality, noting the consistent penetration and uniform appearance that indicated advanced welding techniques and quality control. Japanese tanks used riveted construction for most hull assembly, a technique American and European designers had abandoned years earlier due to the danger of rivets becoming projectiles when struck by enemy fire. The Shermans. All welded construction represented manufacturing sophistication. Japanese shipyards had achieved for naval vessels, but never successfully applied to armored vehicle production. The examination team disassembled the Sherman systematically over the following weeks, removing components in sequence while documenting the process with detailed sketches and measurements. They found construction methods that seemed impossibly efficient compared to Japanese manufacturing practice. The hull was assembled from large rolled armor plates welded together, rather than the smaller plates Japanese factories could produce with their limited industrial presses. The turret casting was a single piece of formed steel, eliminating dozens of welds and potential weak points that characterized Japanese tank turrets built from multiple welded sections. Every major component reflected manufacturing capability that exceeded Japanese industrial capacity by substantial margins. The powertrain examination revealed the greatest disparities between American and Japanese automotive engineering. The Continental R975 radial engine, originally designed for aircraft use and adapted for tank application, produced 400 horsepower from 9 air-cooled cylinders arranged in a radial configuration. Japanese engineers had never seen a tank engine of this type, as Japanese designs used inline liquid-cooled engines derived from truck and tractor designs. The radial configuration provided exceptional power-to-weight ratio and simplified cooling requirements, advantages Japanese engineers immediately recognized but could not replicate with their available manufacturing technology. Engineers measured bore and stroke dimensions, recorded valve timing specifications, and documented the ignition system with its robust magneto that required no external electrical power to operate. They disassembled the engine completely, examining piston rings, connecting rod bearings, and crankshaft journals for wear patterns and manufacturing quality. What they found contradicted every assumption Japanese designers had made about American industrial capability. The machining precision exceeded Japanese standards, despite Americans producing these engines by the thousands in factories operating around the clock. Bearing clearances fell within tolerances measured in hundredths of millimeters. Cylinder bore finish showed honing marks indicating final machining steps Japanese factories could not perform at scale. Piston rings seated properly with minimal break-in required, while Japanese engines typically consumed excessive oil for hundreds of kilometers until rings wore into proper contact with cylinder walls. The transmission examination proved even more revealing about the industrial gap between American and Japanese manufacturing. The Sherman used a synchromesh manual transmission with 5 forward speeds and 1 reverse, incorporating technology Japanese automotive industry had barely begun to explore before the war. Synchromesh mechanisms allowed gear changes without double clutching or careful speed matching, making the tank nearly as easy to drive as a civilian passenger car. Japanese tankers, by contrast, struggled with crash gearboxes that required precise coordination of clutch and throttle to avoid grinding gears or damaging transmission components. The difference in driver training requirements was substantial. Americans could train tank drivers to basic competence in weeks, while Japanese training programs required months to develop the skills necessary to operate their mechanically demanding vehicles. Japanese engineers disassembled the transmission completely, laying out hundreds of components on workshop tables while documenting each part's function and relationship to the overall system. They found helical cut gears that distributed load across multiple teeth simultaneously, reducing stress concentrations that caused Japanese straight-cut gears to fail under heavy loads. They examined synchronizer rings made from bronze alloys that Japanese metallurgists had not developed for this application. They measured shaft alignments and bearing preloads that indicated manufacturing precision Japanese machine shops could not achieve in production conditions. Every aspect of the transmission demonstrated American mastery of automotive mass production techniques that Japan had never successfully implemented, despite decades of attempting to build a modern automotive industry. The final drive examination revealed additional evidence of American engineering sophistication that Japanese designers had not anticipated. The Sherman used spiral bevel gears in the final drive, a configuration that provided smooth power transmission with minimal noise and vibration while handling high torque loads reliably. Japanese tanks employed straight bevel gears that were simpler to manufacture but generated more noise, vibration, and stress concentrations that led to premature failure. The spiral bevel gears in the Sherman final drive showed minimal wear despite the tank having seen combat operations on Saipan before its capture. Japanese engineers calculated that equivalent Japanese components would have required replacement after the same operational period, highlighting the durability advantage American designs enjoyed. Testing protocols expanded beyond static examination to include operational trials that would stress the Sherman's mechanical systems under controlled conditions. Engineers drove the tank through obstacle courses at the Sagami Bay facility, measuring fuel consumption, monitoring engine temperatures, and recording transmission behavior across varying terrain and load conditions. They conducted hill climbing tests to evaluate power delivery and traction control. They ran sustained high-speed trials on improved roads to determine maximum operational range and mechanical endurance. Every test revealed the same fundamental characteristic that made American tanks superior to Japanese designs. The Sherman simply worked without the constant mechanical attention Japanese tanks required. Fuel consumption measurements shocked Japanese observers accustomed to the poor efficiency of their own tank engines. The Sherman achieved approximately 120 liters per 100 kilometers under average operating conditions, while Japanese medium tanks consumed nearly double that amount for equivalent performance. This fuel efficiency advantage translated directly into operational range and strategic mobility. American tank battalions could operate at distances from supply bases that Japanese units could not match, extending American offensive reach while limiting Japanese ability to maneuver forces quickly in response to threats. In a war where logistics determined operational possibilities, this advantage proved decisive in countless engagements across the Pacific theater. Engine cooling system examination revealed another area where American automotive experience exceeded Japanese capability. The Sherman's cooling system maintained stable operating temperatures across ambient conditions, ranging from Arctic cold to desert heat, using a thermostatically controlled system that required no operator intervention. Japanese tank engines frequently overheated in tropical conditions, requiring crews to monitor temperatures constantly and adjust engine speed to prevent damage. The American system reflected decades of civilian automotive development in a vast country with extreme climate variations. Experience Japanese industry had never accumulated through its limited pre-war commercial vehicle production. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The electrical system presented yet another revelation about American manufacturing sophistication. The Sherman incorporated a 24-volt electrical system with a backup generator that could power turret traverse even when the main engine stopped, a feature that seemed like unnecessary luxury to Japanese designers but proved invaluable in combat. Japanese tanks used simpler 12-volt systems that provided minimal power for basic functions, with no backup capability if the main generator failed. American tankers could continue fighting with full tactical capability even after engine damage, while Japanese crews lost critical systems when engines failed. This difference in design philosophy reflected fundamentally different approaches to combat effectiveness. Americans engineered redundancy and backup systems into their designs, accepting additional complexity and cost to ensure vehicles remained combat effective under damage conditions. Japanese designers minimized complexity to simplify manufacturing and maintenance, accepting reduced capability under adverse conditions as an unavoidable trade-off. The air filtration system examination highlighted another critical advantage American designs enjoyed. The Sherman used a multi-stage oil bath air filter that trapped dust and particulates before they reached the engine, protecting internal components from the abrasive wear that destroyed Japanese engines operating in dusty tropical conditions. Japanese tanks used simpler mesh filters that provided inadequate protection, requiring frequent engine overhauls as cylinder walls wore from ingested dust. American crews rarely experienced engine failures from contamination, while Japanese units expected to rebuild engines every few thousand kilometers of operation in harsh environments. This seemingly minor difference in filtration technology had profound implications for operational availability and maintenance requirements that cascaded through entire logistics chains supporting armored operations. Track and suspension examination revealed additional American advantages in durability and ease of maintenance. The Sherman used a volute spring suspension system with vertical volute springs supporting each road wheel independently. This design provided good ride quality and shock absorption, while remaining simple to manufacture and maintain in field conditions. Japanese tanks employed variations of bell crank and coil spring systems that were more complex to maintain and frequently failed under the stresses of combat operations over rough terrain. The Sherman's track used a simple block design with replaceable rubber pads that could be changed in field conditions with basic tools. Japanese tracks used more complex designs that required specialized equipment for repairs, limiting field maintenance capability and increasing dependence on rear area support facilities. Japanese engineers compiled their findings into comprehensive technical reports throughout August and September of 1944, documenting every measurement, observation, and test result in exhaustive detail. These reports, classified as top secret and distributed only to the highest levels of military and industrial leadership, contained conclusions that Japanese officials found difficult to accept. The Sherman represented not merely a superior tank design, but evidence of American industrial maturity that Japan could not match regardless of effort or determination. Every system examined demonstrated manufacturing sophistication, quality control, and design philosophy that reflected decades of civilian automotive development Japan had never achieved despite its rapid industrialization since the Meiji Restoration. The psychological impact of these findings extended far beyond technical circles. Japanese military doctrine since the 1930s had emphasized spiritual strength and warrior spirit as capable of overcoming material disadvantages. The examination of this single captured Sherman provided undeniable physical evidence that industrial capability determined modern warfare outcomes regardless of courage, training, or tactical skill. Japanese tank crews faced American armor with equipment that was obsolete before it reached the battlefield, built by an industrial base that lacked fundamental capabilities necessary for modern mechanized warfare. The realization that Japan had entered a conflict it could not win through industrial production arrived too late to alter strategic decisions, but early enough that senior officials understood the inevitable outcome years before final surrender. Comparison testing between the Sherman and Japanese tank designs began in October 1944 after engineers completed their detailed examination of American engineering. The Imperial Japanese Army provided a Type 97 Chiha medium tank, Japan's most numerous armored vehicle with over 2,000 produced since 1938. The Chiha represented the best Japanese industry could manufacture in quantity, embodying design choices and manufacturing limitations that characterized Japan's approach to armored warfare. Placing it alongside the Sherman for direct comparison revealed the industrial gap in terms impossible to deny or minimize through propaganda or wishful thinking. The Type 97 Chiha weighed 15 tons compared to the Sherman's 30 tons, mounting a 57mm gun that could not penetrate Sherman frontal armor at any practical combat range, while the Sherman's 75mm gun could destroy the Chiha from over a kilometer away. But the technical specifications, already known to Japanese planners, proved less significant than the operational characteristics revealed through testing. Japanese engineers drove both tanks through identical courses, measuring reliability, ease of operation, and maintenance requirements under controlled conditions that eliminated variables of crew skill or tactical employment. The Chiha required constant mechanical attention to maintain operational status. Its Mitsubishi air-cooled diesel engine produced 170 horsepower, adequate for the vehicle's light weight, but prone to overheating under sustained operation. The cooling system demanded frequent monitoring and adjustment by the crew to prevent damage. The transmission, a sliding gear design without synchronizers, required skilled drivers to avoid gear clash and premature wear. Track tension needed daily adjustment as the pins wore rapidly under normal operation. Japanese crews accepted these maintenance demands as normal, having never experienced vehicles that functioned reliably without constant attention. The Sherman, by contrast, operated for days without requiring any maintenance beyond refueling and basic daily inspections. The operational range comparison proved especially devastating to Japanese confidence. The Sherman could travel approximately 190 kilometers on internal fuel, with provisions for external auxiliary tanks that extended range to nearly 300 kilometers. The Chiha managed approximately 210 kilometers maximum range, but only under ideal conditions with careful driving and frequent maintenance stops. In practical field operations, American tank battalions could advance twice as far as Japanese units before requiring resupply, a mobility advantage that translated directly into strategic flexibility and operational tempo Japanese forces could never match. Driver training requirements highlighted another critical difference in design philosophy. American instructors could train competent Sherman drivers in 2 to 3 weeks of intensive instruction, teaching basic driving skills to men who often had civilian automotive experience before military service. Japanese tank driver training required 3 to 6 months to develop the skills necessary to operate the Chiha without damaging the transmission or engine through improper technique. This training time difference meant American replacement crews reached combat units far more quickly than Japanese equivalents, sustaining unit strength despite casualties, while Japanese armored formations steadily declined in effectiveness as experienced personnel were lost and could not be rapidly replaced. The examination team also tested a Type 95 Hago light tank, Japan's other major armored vehicle with over 2,000 produced. The Hago weighed only 7 tons and mounted a 37mm gun adequate for infantry support but useless against any armored opposition. Its Mitsubishi engine produced 120 horsepower, giving the light tank reasonable mobility, but no combat capability against American medium tanks. Japanese tank doctrine had emphasized light tanks for infantry support, viewing tank versus tank combat as unlikely in the Pacific theater, where jungle terrain supposedly prevented large-scale armored operations. This assumption proved catastrophically wrong, as American forces demonstrated that Sherman tanks could operate effectively in terrain Japanese planners considered impassable, using superior engineering to overcome obstacles that stopped Japanese vehicles. Testing of the Hago against the Sherman became an exercise in documenting Japanese inadequacy rather than discovering useful intelligence. The light tank's armor could not resist even 50 caliber machine gun fire at close range, while the Sherman's hull armor stopped all Japanese tank and anti-tank guns, except the largest naval weapons employed in desperate defensive positions. The Hago's maximum speed of 45 km per hour on roads barely exceeded the Sherman's 38 km per hour, while the American tank maintained higher speeds off-road due to superior suspension and track design. In every measurable category, the Japanese light tank proved inferior to the American medium tank by margins that made combat between them effectively impossible. Japanese crews could only hope to ambush Shermans at point-blank range or disable them with infantry-carried explosives, tactics that resulted in catastrophic casualties for minimal effect. Japanese engineers documented these findings with scientific objectivity, measuring performance differences without attempting to minimize the implications. Their reports contained detailed tables comparing specifications, graphs showing test results, and photographs documenting construction quality differences. Senior officers reading these documents could not dismiss the conclusions through appeals to Japanese fighting spirit or tactical superiority. The evidence was physical, measurable, and undeniable. Japan had entered the Pacific War with armored forces that were obsolete compared to American equipment, equipped with vehicles that could not compete mechanically or tactically against enemy armor. Every battle involving tanks had been predetermined by industrial capability rather than determined by courage or skill. The strategic implications extended beyond immediate battlefield effectiveness to fundamental questions about Japan's ability to sustain modern warfare. American industry produced nearly 50,000 Sherman tanks during the war years, while Japanese industry managed approximately 6,000 armored vehicles of all types combined, most of them light tanks or tankettes with minimal combat value. This production ratio of roughly 8-to-1 reflected not temporary circumstances, but permanent industrial capacity differences that could not be overcome through effort or sacrifice. American factories operated with electrical power, machine tools, skilled workers, and raw materials in quantities Japan could never match, building weapons in climate-controlled facilities, using precision manufacturing techniques, while Japanese workshops struggled with power shortages, inadequate tooling, and increasingly desperate material substitutions. The captured Sherman sat in its testing bay at Sagami Bay through the winter of 1944 and spring of 1945, as American forces advanced relentlessly across the Pacific. Each island captured brought American bomber bases closer to the Japanese home islands, with B-29 superfortresses beginning systematic destruction of Japanese industrial capacity through incendiary raids that consumed entire cities. The same industrial weakness that prevented Japan from building reliable tanks now prevented effective response to strategic bombing. Japanese aircraft production, already inadequate to replace losses, declined further as factories burned and raw materials became increasingly scarce. The industrial spiral that had begun with pre-war limitations accelerated into complete collapse as American material superiority translated into total domination of sea, air, and land. Engineers at Sagami Bay continued their examination work even as the strategic situation deteriorated beyond hope of recovery. They tested the Sherman's gyrostabilizer system that allowed gun laying while moving, a capability Japanese tanks completely lacked. They examined the power traverse mechanism that let American gunners track targets quickly, while Japanese crews manually cranked their turrets. They studied the gun sight optics that provided clear target images at ranges where Japanese optics became useless. Every system revealed American advantages that compounded into overwhelming battlefield superiority. A Sherman crew could spot Japanese tanks first due to better optics, maneuver into firing position while maintaining gun alignment through the stabilizer, quickly traverse onto target with powered controls, and destroy the enemy vehicle with the first shot, while the Japanese crew was still manually cranking their turret toward the threat. The The psychological weight of these discoveries affected Japanese engineers personally and professionally. These men had dedicated their careers to building weapons for their nation, believing that Japanese craftsmanship and attention to detail could compensate for material limitations. The Sherman proved that belief tragically wrong. American mass production techniques they had dismissed as crude and unsophisticated produced tanks that were simply better in every meaningful way. The industrial methods they had considered inferior to Japanese precision craftsmanship delivered superior results through approaches Japanese industry could not replicate. The recognition that their entire professional understanding had been based on false assumptions about manufacturing and design philosophy came too late to change anything, but forced them to acknowledge uncomfortable truths about Japanese industrial capability. By August 1945, American occupation forces were preparing to land on the Japanese home islands when the atomic bombings of Hiroshima and Nagasaki, combined with Soviet entry into the Pacific War, forced Japanese surrender. The invasion that would have employed thousands of Sherman tanks against desperate Japanese resistance never occurred, sparing both sides the casualties such fighting would have inflicted. The captured Sherman at Sagami Bay survived the war intact, its testing program incomplete as Japan's military structure collapsed around it. American technical intelligence teams found the tank along with the comprehensive reports Japanese engineers had compiled, documents that provided fascinating insight into how Japanese military leadership had understood their industrial inadequacy, yet continued fighting long after rational assessment indicated defeat was inevitable. The reports revealed that Japanese officials recognized American industrial superiority as early as mid-1944, more than a year before final surrender. The decision to continue fighting despite this knowledge reflected complex factors including institutional momentum, fear of unconditional surrender terms, and belief that inflicting sufficient casualties might force negotiated peace terms. The examination of American tank technology had proven that Japan could not win through military means, but political and cultural factors prevented acceptance of that conclusion until atomic weapons and Soviet invasion made continued resistance obviously futile. The human cost of that delay, measured in hundreds of thousands of Japanese and Allied casualties who died in battles fought after Japan's defeat, had become mathematically certain. The industrial lessons Japanese engineers learned from examining the Sherman influenced post-war Japanese automotive development profoundly. When Japan rebuilt its civilian economy during the 1950s and 60s, automotive engineers consciously studied American mass production techniques and quality control methods. They visited American automobile factories, examined American manufacturing processes, and systematically adopted practices that had made American industry so formidable during the war. The result was transformation of Japanese automotive industry from wartime inadequacy to post-war excellence, with Japanese manufacturers eventually surpassing American companies in quality and reliability through disciplined application of principles they had first encountered while examining that captured Sherman tank. The bitter irony that Japanese engineers learned lessons from American automotive superiority that they later used to dominate global automobile markets was not lost on historians examining this transformation. The same manufacturing principles that had built 50,000 Sherman tanks with exceptional reliability became the foundation for Toyota production system and other Japanese manufacturing philosophies that revolutionized global industry. The defeated nation studied its conqueror's methods with humility and determination, systematically correcting weaknesses the war had revealed so brutally. Within 3 decades of surrender, Japanese automobiles were recognized worldwide as setting standards for reliability, quality, and manufacturing excellence that American companies struggled to match. The captured Sherman tank itself was eventually scrapped during the chaos of post-war reconstruction. its metal recycled as Japan rebuilt from devastation. But the technical reports Japanese engineers compiled survived in archives, preserved as historical documents that provided unique perspective on how defeated powers perceived Allied technological advantages. These reports, written by intelligent and technically competent engineers, demonstrated that Japan's defeat resulted not from lack of skill or effort, but from fundamental industrial capacity differences that could not be overcome through courage or determination. The recognition that modern warfare demanded industrial capability more than martial spirit represented painful acknowledgement of reality, but also provided foundation for post-war economic policies that prioritized industrial development over military power. The story of Japanese engineers examining a captured Sherman tank illuminates broader truths about the Pacific War that extend beyond tactical or operational military history. Japan entered conflict with the United States based on fundamental miscalculation of American industrial power and willingness to employ that power decisively. Japanese planning assumed that early victories would force negotiated settlement before American industrial capacity could be fully mobilized. This assumption proved catastrophically wrong, as American production reached levels Japan could not match in any category of military equipment. The examination of one tank crystallized this disparity in terms Japanese engineers could measure and document, providing microcosm of the larger industrial contest that determined the war's outcome. The human dimension of this story resonates across decades since the war's end. Japanese engineers who examined the Sherman were not evil men but patriots who had believed their nation's propaganda about American industrial weakness and Japanese spiritual superiority. Their careful documentation of American technological advantages represented professional honesty that contradicted official narratives about the war's progress. These men understood Japan was losing an industrial war it could never win, yet continued their work because duty and honor demanded they contribute what they could despite inevitable defeat. Their reports, filed away as the empire collapsed around them, testified to human capacity for maintaining professional standards even when faced with the futility of all effort. The broader lesson that industrial capacity determines modern warfare outcomes, while courage and skill remain necessary but insufficient conditions for victory, echoes through subsequent conflicts. Nations entering wars without adequate industrial base to sustain prolonged combat inevitably lose regardless of initial advantages or tactical proficiency. The Sherman tank examination demonstrated this principle through mechanical systems that could be measured, tested, and compared objectively. American industrial maturity translated into reliable vehicles that kept running when needed most, while Japanese industrial limitations produced equipment that failed under stress, despite best efforts of skilled workers and dedicated engineers. This difference, repeated across every category of military equipment, decided the Pacific War's outcome as certainly as any battle or campaign. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.